Hey, I'm Kyle.
I'm Joey.
We're doing example problem 5A.11. A step drum having a mass of M and a radius of gyration about its center O of KO is attached to a smooth shaft passing through its center. A cable wrapped around the outer radius of the drum is attached to point A, shown there. A second cable is wrapped around the inner radius of the drum. With this cable pulled over, an ideal pulley is attached to block B, which is shown right there. Assume that the cables do not slip on the drum and the system is released from rest. And then we are supposed to determine the angular acceleration of the drum on release.
Okay, so for step one of this problem, we have to draw our free body diagrams for each mass given. So this is the free body for mass A. Here's the free body for mass B. And then this is the free body diagram for mass C, or the big M mass. And then step two is to draw a coordinate system. So all of these free body diagrams can be fit into one coordinate system with just regular I, J components. So we're listed with givens. So we have mass A is 10 kilograms, mass B is 30 kilograms, capital M mass is 20 kilograms, the small radius, the inner radius is 0.2 meters, the outer radius is 0.4 meters, and KO is 0.25 meters. So for step three of this problem, we have to list out the forces. So for the first free body, we have the weight force of A, so name that WA is equal to negative mass A times gravity in the J direction. And then we have the tension force at A, so that is listed as TA equals FTA in the J direction. That is positive because it is going up. So in the second free body, we have the weight force of B going down and the tension force going up. So we have WB which is equal to negative mass of B times gravity. And then we have TB, which is equal to FTB, which is just the force and tension B. And these are both in the J direction as well. Now for our third free body diagram, we have a few more equations. So we will start with the weight force going down. We'll just label that W capital M, which equals negative capital M times gravity in the J direction. And then we have the force and tension at B. So that would be TB is equal to FTB, that is in the I direction, that is to here. Then we have the tension in A, so TA is equal to FTA in the J direction. And then we have our reaction forces at the pin in the center of the wheel. So we have Rx, which is equal to Rx in the I direction. And then Ry, which is in the J direction. So this is a list of all of the forces that are acting on this diagram, or on each end.
Okay, so for step 4, it says to write out the acceleration in vector form for every mass. So for mass A, it will be AG is equal to AGXA in the I component plus AGYA in the J component. For mass B, it's going to be vector AG is equal to AGXB in the I plus AGYB in the J component. And then for the mass of the drum, there's not going to be any acceleration since it is on the fixed point O, so the acceleration in the X and Y will both be 0. Step 5 is sum of the forces is equal to mass times acceleration. And we'll need to do that for both mass A and mass B. So the first step is to write out all the forces for mass A. And then set that equal to mass of A times the acceleration of A from step 4. And then we will separate that into the 2 scalar components. The first being I. And since there's no forces in the I component, there'll be no scalar equation. And then for J, it's negative MA times gravity plus F from tension A is equal to MA times the acceleration of mass A in the Y component. And that will be our first scalar equation. And then we'll do the same process for step B, for mass B. And then we'll need to do our 2 scalar equations for mass B, and for the I component, it will also be 0. For the J component, it will be negative MB times gravity plus FTB is equal to mass B times the acceleration of B in the Y component. And that is step 5.
So the next step is step 6. And we can tell that this is a case 2 of Euler's equation. So the equation would just become the sum of the moments equals IO times the angular acceleration alpha. So looking at this, we will look at the free body diagram for the disk mass, and we will see which forces on this diagram will cause a moment about point O. So looking at this, no inline forces with the point O, which is right here, are going to cause a moment about this. So the only things that will are the tension force at B and the tension force in A. So the equation would be sum of the moments is equal to IO, which is equal to MKO squared. So we can write sub in MKO squared times alpha is equal to tension at B would cause a clockwise moment, so that would be negative, and tension A would cause a counterclockwise moment, so that is positive. So it would be negative FT B times the distance away, which is in tension B, it's little radius, so little r. And that would be plus FTA times its distance away, which would be big R, the full radius to the outside disk. Okay, so now we can write our scalar equation, and then that would be in the k direction. So, which would be MKO squared times alpha Oh, I did not mention that these are both in the k direction, excuse me. There we go. So now scalar equation k would be MKO squared times alpha is equal to negative FTB times R plus FTA times big R. And that is your, let's see, that's third scalar equation. So now we can go to step 7. Which isn't always needed, it's only needed for certain problems like this one, where we don't know the accelerations at point A and point B. So we can write, these are chapter 2 equations, by the way. So the first equation we will do is the acceleration at point B on the wheel with respect to point O. Because we know that the acceleration at point O is 0 in both the I and K direction, or I and J direction, excuse me. So we have acceleration at B is equal to A, O, plus alpha cross R B slash O angular velocity squared times alpha B slash O. And then the scalar form of this equation would be I direction. That gives AB is equal to AO is a fixed point, so that drops out, becomes 0. So it's just alpha, which alpha cross r b slash o gives a negative alpha times the little inside radius. And then that is a scalar equation 4. So then now we will do the acceleration at point A, which is here. So we have acceleration at A is equal to acceleration at point O again, because that's the acceleration that we know to be 0, plus alpha cross r a slash o minus angular velocity squared times r a slash o. The scalar form of this would be in the j direction because the mass A is being pulled directly down. So j, which is acceleration at A. We've established that this is 0. So you do the cross product here. And that gives you this to be equal to the negative angular acceleration times your big radius, capital R. And this is scalar equation number 5.
Okay, so after we solved all of our scalar equations from steps 1 through 7, we are going to plug them into each other to be able to solve for alpha. And since point A is connected to mass A by a cable, we can determine that AGYA is equal to AA, and then mass B is also connected to point B by a cable, so AGYB will be equal to AB. So the first thing we're going to do is we're going to plug scalar equation 5, AA, into scalar equation 1 for AGYA. And then we're going to solve for this in terms of FTA. And then the next thing we're going to do is we're going to plug in scalar equation 4 into scalar equation 2, AB into AGYB. And then we're also going to solve for this in terms of FTV. And then now that we have these two new equations, we can plug in FTA and FTB into scalar equation 3 to be able to solve for alpha. And then when you solve this algebraically, get everything in terms of alpha, it will come out to alpha is equal to MA times G times R minus MB times G times little r, all divided by MKO squared plus MA big R squared minus MB little r squared. And then when we plug in our given values into this equation, the answer for alpha will come out to be negative 11.89 radians a second squared, all in the k direction. And that is the answer to our problem.